Good morning, AP Stats kids. Hopefully you've had a chance to look at your 11.1, 11.2 review. That's what I'm going to be going over right now. If you have that, it was passed out on Thursday. So looking at this first question, it says determine if the number of flavor preferences is the same or uniform throughout. So we're looking at the number sold for each of these 4 different types of flavors. Since there is only one variable, that being the flavor, and there was only one sample that was taken from the population, now you know that it's supposed to be a goodness of fit test. So that first problem says, like keywords, do they have a preference of flavors? Are they uniform? That gives us our chi-squared goodness of fit test. Okay, so the distribution of flavors being uniform would be your null hypothesis. So you see that as a distractor for number 2. There is no flavor preference is the same thing as saying that it's uniformly distributed. They're asking you about the alternative. The opposite of that would be that there is a flavor preference. So usually when we're writing those ho and haws, like you would say like the P sub flavor is 1/4. Your ha should be at least one of the P sub flavors is not 1/4 or 25%. That's what E is asking kind of, but they are specifically saying each one is wrong. Like they all don't equal 25%. But that's not true. Only one of them has to be wrong for us to be able to fail. Sorry. It's okay. All right, guys. So then it looks at the expected counts. The expected counts should be our total, which in this case was 80, multiplied by that probability of success or probability that they're all the same. You could either do 80 divided by the 4 categories, or you could do 80 multiplied by 1/4. You can do the 80 multiplied by 1/4. Or you can do 80 divided by 4. So at least that gives you all of the same 20-20-20 breakdown. And then for the degrees of freedom, you can see they have other distractors if you forget. Our degrees of freedom should be the number of categories minus 1. So that's your 3 degrees of freedom. On the next question. On the next questions 4 through 7, you have a random sample of 100 traffic tickets. The tickets are being classified according by the race of the driver. And so we're trying to see if they're broken down the same as the city's population. So we have prior percentages and we're checking to see if they match up to this new distribution. So that's another chi-squared goodness of fit test. This one's not for uniform distributions, but trying to match to see if it is a good fit for that same data. So first, we know that there's 100 total traffic tickets. And since we know what the percent for each race is supposed to be, to find our expected values, I would do that 100 times each one of those percents. That's where I got the 60, 30, 3, and 2 from. After that, you're supposed to go through and look at what conditions you need. For our conditions for a chi-squared test, we still have random, we have independence, and then we have now, instead of normality, we need large counts. Well, those large counts, number 1 or Roman numeral 1 is a distractor for sure. They think you're going to pick that one, but you need to read carefully. It says the sample is large enough so that all observed counts are greater than 5. We don't need that. We need our expected counts to be at least 5. So if you picked 1, that's wrong because the word observed needed to be the word expected in order for that to be true. For Roman numeral 2, we do need independent samples. Perfect. Number 3, we don't need anything about normality for chi-square tests. So that one's wrong. Only B. For the component, hopefully you have that calculation. They even gave you the formula. They're just trying to see if you can plug in and get it right. And then for 6, you pretty much had to do all of that by hand or in your calculator. Remember that contraband or I said contraband, it's contributions list. Gives you all of that. And that also helps you, if you've done it in the calculator, to know what the actual p-value is. This p-value is super teeny tiny. So that p-value being less than 1% is also C. On the back side, if you're looking at those, now you have a chi-squared test for association or independence. There's a couple different ways that you could list your hypotheses for this one. I went with, for my null hypothesis, there is no association between color preference and gender. You could have said that they're independent variables. For Ha, there is an association between them. Just make sure that you have context for this problem. You know, if you're saying that they are dependent on one another, you need to mention the variables. The two variables in this one were the color preference and the gender. So then you need to check all your conditions. The random condition should be met. Independence condition is also met. Our law of large counts is met. Explain all those in detail. The large counts was not met. There's a weird condition where it says like, oh, you can continue as long as 1/5 of the numbers are greater than 5, or 20% of them is the only one that fails. Since 1 out of the 6 didn't meet that requirement, we could keep going. That's not even in our textbook, so whatever. But that 4.6 being less than 5, technically based on our textbook, says you shouldn't keep going. I said proceed with caution because they told you to perform the calculations and report a conclusion. So that means like you should continue. For the chi-squared independence test, the degrees of freedom should be 2. Again, that formula was row minus 1 times column minus 1. Calculate your chi-squared Calculate your chi-squared test statistic, which should be 2.697. And then that p-value also from your calculator should be 0.2596. All right. And I showed work. Remember, all that's nice, not necessarily required. If you just wrote the test statistic and the p-value, you'd be all right as long as you get the correct conclusion. So since our p-value was greater than our alpha, we would fail to reject our null hypothesis. There is not enough evidence to suggest that the color preference is dependent on gender. All right. On this next one, Mr. Dorky, he is going to go through and he wants to know if his random digits of logarithms have a last digit that is random. So another goodness of fit test, this one for uniformity, that word, like do they appear equally often, makes us know that we're supposed to do that. So since there are 10 digits, 80 divided by 10, we were expecting 8, 8, 8, 8, 8. For this one, define your piece of integer. That's your proportions of each integer showing up. Your hoe should be that the digits are random, like each one of them show up 1/10 of the time. Or you could say something like the integers are equally likely. Your ha should be that they're not random, or at least one of those piece of integers does not equal 1/10. For the random condition, it didn't say that you had a random sample. I'm assuming that if he's going through the list, he's gonna select them randomly, or maybe, I don't know. For independence condition, like does each one of our ones that he's chosen affect the next one that he chooses? Probably not. All the expected counts were 8. That's greater than 5. Continue. Chi-squared goodness of fit test. Degrees of freedom should be 9 since there's 10 digits. That test statistic was 6 and the p-value was 0.7399. So remember when we were looking at our chi-squared, they're all skewed right. They're less skewed right as you increase the degrees of freedom. As you increase the degrees of freedom, it peaks at higher values. So if you are looking at a degree of freedom of 9, I'm pretty sure it peaks at 8. And then, so if you're at 6, that's why we have such a large p-value. All chi-squared tests are right-tailed, okay? So don't do the subtract -1 or anything like that to figure out the probability. It is that large of a probability. So we really want to fail to reject hoe. So that gives us evidence that that table of logarithms, that last digit isn't appearing randomly. All right, hope that helps. See you soon.